Hello, students. How are you all? So, I'm back with another chapter called Alternating Current. Today, we are going to solve numericals based on these chapters. So, we are going to solve all previous NEET questions as usual. Let's get started without any delay. So, the very first thing I've given some note point to understand how to find out why average value and RMS value of any given quantity. Here, y is a function which is varying with respect to time. Then, to find out average and RMS, these are the formulas. So, we have to remember this formulas to find out average and RMS for. So, any kind of alternating quantity they used to give in question. Okay. Okay. Okay, so the very first question is based on AC voltage applied to a resistor. Okay, first one, the RMS value of potential V shown in the figure. So they are given some voltage variation with respect to time graph. We have to find out its RMS value. Which formula I have to use to find out RMS? Second one or first one? Second formula we have to use. Let's try to answer this. So this is the graph that they have given. So our RMS value we have to find out it for one complete time period. You can observe these limits. It's 0 to t. So let's talk about them. So what is the value of potential from 0 to t by 2 and from t by 2 to t? That's what we have to answer. So value of V is equal to V naught for 0 less than or equal to t less than or equal to t by 2. It means, so in this region in between 0 to t by 2 the value of potential is V naught, that's the meaning. But in between t by 2 to t value of potential is 0. You can observe this. For 0 less than, sorry, it's t by 2 less than or equal to t less than or equal to t. Okay, so this is the value of voltage for different time periods. Now formula for vrms is equal to, as I told you earlier, it's integral 0 to t v square dt divided by integral 0 to t dt. So let's divide this. 0 to t we can divide it as 0 to t by 2 and t by 2 to tt. 0 to t by 2. From 0 to t by 2, what's the value of potential? V naught. So it's going to be V naught square dt plus from t by 2 to t, value of potential is 0 into dt divided by integral 0 to t dt. So let's integrate them. So this one is going to be 0. V square, V naught square is a constant magnitude that will comes outside, and V naught square integral dt is t. Limits are from 0 to t by 2 divided by integral dt is t. Limits are from 0 to t. So finally it can be replaced as V naught square by, so limits, this is t, integration is t. So V naught square into t by 2 divided by, substitute upper limit minus lower limit, and we are going to get this. So here also t. So this t will get cancelled, and this is vrms square, because I haven't given it is whole power 1 by 2, right? So left side it should be vrms square, and it's going to be V naught square by 2. Then vrms alone is V naught by root 2. This is the answer. Which option matches? Option C is the correct answer for this question. Understood the process? Okay, next one. In an AC circuit, IRMS and I naught are related as. General relation between IRMS, VRMS, VM and IM are Vm is equal to root 2 times of Vs, where Vs is RMS and this Vm is maximum value. So let me expand this. I'll write down it is clearly. So V maximum is equal to root 2 times of Vrms. Similarly, I maximum is equal to root 2 times of IRMS, or IRMS is equal to I maximum divided by root 2. I maximum in the sense I not they have given. So which option? Option D is the correct answer. Next question number 3. So before going to this solve this question, I would like to give one point. So we have two different types of supplies, right? One is AC supply and another one is DC supply. So AC supply flows on the surface of the conductor, on the surface of the conductor, whereas DC flows through the complete area, through the complete area of the conductor. Let me show you the difference. What is the difference between these 2 points? So just observe this diagram so that you can understand what is the difference between AC flow and DC flow. So DC flows throughout the cross-sectional area of the conductor, whereas AC flows only on the outer surface. That is the reason this conductor is split into n number of small conductor, so that we can achieve maximum current. This is how it's going to be changed. They'll convert this thick conductor into thin conductor. Actually, this process is called as a skin effect. So if AC flows only on the outer surface area, and that is called as skin effect. That's the reason. So they are going to divide these conductors into n numbers and they'll supply AC. Then we can achieve maximum current flowing through the conductors. This is how all the conductors are divided. So this is the suitable for AC and this conductor is suitable for DC. So let's solve the question. Two cables of copper are of equal lengths. One of them has a single wire of area of cross section A, while the other has 10 wires of area of cross section A by 10 each. Gives their suitability for transporting AC, give their suitability for transporting AC and DC. Okay, as I said earlier, which is suitable for DC. So this conductor, thick conductor, is suitable for DC. So n number of conductors divided into small conductors and merged. Okay, or this is arranged in as a one conductor, that is suitable for AC. Which option matches? Okay, here it is. Option B is correct, I guess. No, option B. Yes, here it is. Only multiple stands for AC. Next, either for DC. Yes, we can use anything for DC because DC flows through the complete area of cross section, right? So you can use both of them. But second case is multiple conductors are useful only for AC. So which option matches? Option A is the correct answer. Understood? So as DC flows through complete area of cross section, you can use any one of them. Let's move on to the next topic. AC voltage applied to an inductor. Okay. So let's solve question number 4. A coil of self-inductance L is connected in series with the bulb B as shown, and an AC source. Brightness of the bulb decreases when. Okay. Let me draw the circuit. So this is the circuit. Whenever supply voltage is given, some voltage will drop across the inductor, remaining voltage drop across the bulb. So if the voltage which is across the bulb, if it is greater than voltage drop across the inductor, then bulb glows brighter. So VB, if VB is greater than VL, let's say total voltage is VS, then bulb glows brighter. Bulb glows brighter. Then now what should I have to do? I have to decrease voltage across the bulb. How can I decrease voltage across the bulb? By increasing voltage across the inductor. How can I increase voltage across the inductor? Just check it out. So a capacitance of reactance XL is equal to XC is included in the same circuit, does not change. No need of a capacitor of XL is equal to XC, because if XL is equal to XC, complete voltage across this XL and XC will be 0. Total voltage will appear across bulb, then it will glows much more brighter. So that is not suitable. So next, an iron rod is inserted in the coil. It may be possible because if I place some iron rod in the coil, so as it is carrying variable current, definitely it will magnetizes this iron rod. So magnetizes in the sense all the dipoles will align in the same direction. So this iron rod gets magnetizes. If it gets magnetizes, then what happens to magnetic field? In this case, magnetic field increases. If magnetic field increases, then what happens to XL value increases. That is inductive reactance. If inductive reactance increases, then what happens to VL also increases. If VL increases, definitely VB decreases. This is how we can achieve to reduce the brightness of the bulb. So if iron rod inserted, what happens? So rod magnetizes. So if rod magnetizes, then what happens? Magnetic field increases, so which increases inductive reactance. Due to this increasing inductive reactance, what happens to VL increases, so which reduces B. That's why bulb brightness decreases. Got it? So option B is the correct answer, suitable answer for this question. Understood? So just observe option 3 and option 4 also. So they're saying a frequency of the AC source is decreases. If you observe option C, if frequency decreases, then what happens to XL? XL is proportional to frequency, right? XL also decreases. If XL decreases, VL decreases. If VL decreases, VB increases. Voltage across the bulb increases. Then is it possible to achieve, is it possible to decrease the brightness of the bulb? No, it is not possible. Similarly, option D. If you observe option D, number of turns of the coil reduced. If number of turns of the coil reduces, then what happens to self-inductance of the coil? Decreases. If self-inductance decreases, then VL decreases. Then VB increases. This is also not suitable option for decreasing the brightness. So I'll explain A once again. So if I add one capacitor, so just observe this circuit. So if I add one capacitor whose capacitive reactance is the same as inductive reactance. So this is the supply voltage that I am giving. So if this is XL and this is XC, if XL is equal to XC, these two will get cancelled out and it can be replaced as a short circuit. So this is going to be circuit. So as there is no any opposition, complete total voltage is given to bulb. So what happens to brightness? Brightness increases or decreases? Brightness increases. Okay. So that's why remaining three options are wrong. Only first option B is correct. Understood? So when you are deciding what one option is correct or wrong, You should be in a position to understand why the other three are not suitable for this question. Got it? This is the procedure to cross check. So let's move on to the next question. The current I in an AC circuit with inductance coil varies with the time according to the graph given below. Okay, so which one of the following graphs gives the variation of voltage with time? Okay, we can answer this question with the help of equation itself. So what's the voltage across inductor formula? So VL is equal to minus L into di by dt, right? So this is voltage across the inductor. So if you just differentiate current with respect to time, so observe from just let's divide this into 0 to t by 2 and t by 2 to t like this. So if you observe from 0 to t by 2, is the slope is positive or negative? 0 to t by 2. Slope is positive. If slope is positive, then what's going to be VL? VL is going to be negative or positive? It is going to be negative. Okay, because I have already negative, no? Negative of dl by dt is positive, and we are going to get VL as negative. So, and it starts from some maximum value. So which option is suitable for this? Definitely option A is the suitable answer. This is one way of answering. Another way is always voltage across inductor leads the current by 90 degrees. Just observe this. So if this is the waveform I have for current, then voltage is going to lead it by 90 degrees. This is the exact way of representation. Voltage leads the current by 90 degrees. So this is the actual representation of voltage with respect to time and current with respect to time. So because here V leads I by 90 degrees. So voltage leads the current in inductive circuit, voltage lags the current in capacitive circuit. This is a clue point to answer this kind of question. Got it? So let's solve numericals based on AC voltage applied to capacitor. Okay. So a 40 microfarad capacitor is connected to a 200 volt 50 hertz AC supply. The RMS value of current in the circuit is nearly okay. Super. Sixth one. So whenever they have given supply voltage as a 200 volt and 50 hertz, that is a source supply voltage, AC supply. This is how they did mentioned, which is 200 volt 50 hertz. So you can take blindly it is as RMS voltage. Okay, supply voltage is always RMS voltage. If it is peak value, definitely they will mention it in the question itself. So what's the value of capacitors they have given? So C is equal to 40 microfarad. So first of all, find out XC. XC is equal to 1 by omega C, right? So 1 by omega. Omega is 2 pi F. F is 50 hertz into C. Okay. So how to find out IRMS? IRMS is equal to VRMS divided by XC. XC is the capacitive reactance. General form I is equal to V by R, like that we used to write down, right? So you can apply it here also. So here IRMS is equal to VRMS by XC. Let me substitute. IRMS is equal to VRMS is 200 volt, or else first of all let me substitute the formula. So VRMS divided by 1 by omega C. This omega C goes to numerator, so we can replace it as VRMS into omega C. Omega is 2 pi FC, so 2 pi F into C. So VRMS is 200 into 2 into pi into F is 50 hertz. Capacitance is 40 into 10 power minus 6. So if you solve this, you are going to get approximately 2.51 ampere. That's the answer. Which option? Option C is the suitable answer. Okay, let's move on to the next question, number 7. So in question number 7, a small signal V of t is equal to V naught sine omega t is applied across an ideal capacitor. Okay, so V of t is equal to V naught sine omega t. Here V of t is called as RMS voltage and this V naught is called as maximum value or peak value of the applied voltage. Okay, now it is applied to a pure ideal capacitor as I told you earlier. So in inductor current lags the voltage, but in capacitor current leads the voltage by 90 degrees if they are pure inductor and pure capacitor. Now as it is given to capacitor, then current lags. So I of t is going to lags, sorry, I of t leads. In capacitor, I of t leads V of t by 90 degrees. Which option for question number 7? Are you guys following? Let me read it out, all the options. Current I of t is in phase with the voltage. No, it is not correct answer. Current I of t leads voltage by 180. No, it leads by 90 degrees. Next, current I of t lags voltage by 90 degrees. This is also wrong answer. Now only one, we are left with one option, that is the correct suitable answer. Let me read it out. So over a full cycle, the capacitor does not consume any energy from the voltage source. Yes, it is for the first half cycle it will stores. Next half cycle it will releases. That's all. That's the purpose of capacitor, right? Okay, let's move on to the next one. In an AC circuit, an alternating voltage 200 root 2 sine 100 t volts is connected to a capacitor of capacity 1 microfarad. The RMS value of current in the circuit is, okay, so we did solve this one again. So V of t is equal to 200 root 2 sine 100 t. So what's the relation between maximum value and RMS value? So Vm is equal to root 2 times of Vs, right? So root 2 Vs. Then what about Vs? Vs is Vrms here. So what about Vs? Vs is equal to Vm by root 2. What's the value of Vm? Vm is the maximum value of voltage. Maximum voltage is 200 root 2 divided by root 2. Will get cancelled out. So what about capacitance? Omega C we have to find out, right? Omega C is equal to 2 pi f c. So 2 into, now if you cross check here, this is completely omega, right? So they gave the value of complete omega itself. So omega value is 100 into capacitance is 1 microfarad, that is 1 into 10 power minus 6, which is equal to 10 power minus 4. So IRMS is equal to VRMS divided by XC, where XC is 1 by omega C. So VRMS is equal to 1 by omega C, which is equal to omega C into VRMS, where omega C is 10 power minus 4 and VRMS is 200. Which option is suitable here? So 1 0 will get cancelled. Answer 20 milliamperes is the suitable answer. Option D is the correct answer for this question. Got it? Next, let's move on to the next one. A capacitor of capacity C has reactance X. If the capacitance and frequency become double, then reactance. So, okay. So, ninth solution. What is the formula for reactance? Capacitive reactance of the capacitor is Xc is equal to 1 by omega C, where omega is 1 by 2 pi fc. So XC is inversely proportional to both frequency and capacitance. They said both are being doubled. If both will become double, then what happens to XC? XC will reduce us by 4 times. So F and C are doubled. That means increasing or decreasing? Increasing. So if these two values increases, then what happens to XC? Decreases. If F and C are doubled, F is doubled, C is also doubled, then total value is 4 times. Then frequent XC is going to be decreases by 4 times. Which option is suitable here? Option C is the correct answer. Understood? So these are the numericals based on AC supply is given to pure resistive, inductive and capacitive circuits. Now we are going to solve numericals based on AC voltage applied to a series RLC circuit. Let's start. Okay, so now question number 10. A series RLC circuit is connected to AC voltage source. When L is removed from the circuit, the phase difference between current and voltage is pi by 3. Okay, so if L is removed, now I am going to left with only resistor and capacitor. So supply voltage is applied like this. Then how to find out power factor with the help of these two? So they gave a phase difference, right? Phase difference is phi. Now tan phi is equal to reactance by resistance, that is XC by R. This is the actual formula of tan phi. Okay, so which value they have given value of phase difference, that is pi by 3. Okay, let's keep it as it is. Next, if instead C is removed from the circuit, the phase difference is again pi by 3. Okay, in this case they are removing C, so it means only inductor and resistor are present. So this is the supply voltage R and XL. Again tan phi formula is reactance. Here reactance is going to be inductive reactance divided by R. Again phase difference is pi by 3. So as here left side tan pi by 3, right side tan pi by 3, you can just equate them. Let's say this is 1 and this is 2. Equation 1 is equal to equation 2 here. So it's going to be XC by R is equal to XL by R. R will get cancelled out. Then XL is equal to XC. It means the circuit is under resonance. Resonance in the sense inductive reactance is equal to capacitive reactance. Now what is the question? The power factor of this circuit. See, if XL is equal to XC, then circuit is going to be remain with only resistor. Okay, so this is the final circuit. This is what I am left with. So if the circuit is left with only resistor, then power factor of the circuit is equal to 1. There is no any phase difference. Phase difference between voltage and current is going to be 0. So then formula for power factor is cos phi. Cos phi is equal to 1. For a pure capacitive circuit, power factor is 1. For pure inductor and for pure capacitor, power factor is equal to 0 because phase difference between voltage and current is going to be 90 degrees in that case. Okay, next question number 11. A circuit when connected to AC source of 12 volt gives a current of 0.2 ampere. The same circuit when connected to DC source of 12 volts, it gives a current of 0.4 ampere. The circuit is okay. Super. So now in this case they given first AC source is 12 volts gives a current of 0.2 ampere. So AC source given in the sense we don't know what kind of elements are connected, so we have to treat it as a impedance. So what's the formula for impedance? Z is equal to V by I. Value of V is 12 volts and current is 0.2 ampere. So impedance in the circuit is 60 ohms. Okay, so this is the first case. In the second case, so the same circuit when connected to DC source 12 volts. So DC source in the sense only resistor is present. Again V by I. Value of voltage is 12. Current is 0.4 amperes. Then it is going to be 120 by 4. So 30 ohms is the resistance. This is second case. Okay. Now how to find out power factor? Power factor formula is cos phi is equal to R by Z, where R is 30, Z is 60, which is equal to 1 by 2. Then phi is equal to 60 degrees. So 60 degrees lags the voltage. Okay, as 60 degrees lags voltage, then it is definitely a inductive circuit. Okay, so it's going to be combination of L and R circuits. L and R circuit. LR series circuit. You can answer like that. LR series circuit. Option A is the correct answer. Okay, let's move on to the next one. So which of the following combination should be selected for better tuning of an LCR circuit for communication? So for better tuning, so we have to cross check with the quality factor. So the formula for quality factor is Q is equal to 1 by R root of L by C. This is for series combination, quality factor. And for parallel combination, it's going to be R root C by L. So this is for parallel combination. Now we are solving numericals based on series combination, right? Okay, so that means which formula I have to choose? So Q is equal to 1 by R root of L by C. Okay, so let's start with option A. So whatever the option which is having more quality factor, that is the option we have to choose for better tuning of LCR circuit. Okay, so let's say option A. So Q is equal to 1 by R value is 20, root of L is 1.5, and C is 35 microfarad. So approximately you are going to get it is as 10.35. So this is how you have to cross check with remaining also. This is Q1, and option B, Q2 is going to be approximately 9.43, and Q3 is equal to 22.77, and Q4 is equal to 7.30. You have to substitute and cross check. That's the only way we have. So for which option we have more quality factor? Option C. Okay, option C is the correct answer. Let's move on to the next one. A series RC circuit is connected to an alternating voltage. Considers two situations: when capacitor is air filled and when capacitor is mica filled. Current through the resistor is I and voltage across the capacitor is V. Then what happens? So let's write down formula for current. 13. So as it is a combination of resistor and capacitor, first of all we have to write down impedance. This is R and XC. So impedance of the circuit, total opposition for current flow, is R square plus XC square. So where XC is root of R square plus 1 by 2 pi FC square. This is impedance. Now what's the current flowing through the circuit? Current I is equal to V0 by Z, where V0 divided by root of R square plus 1 by 2 FC whole square. One thing we know that if capacitor is air filled, capacitance C is equal to epsilon naught A by D. If it is some other if it is filled with any dielectric, okay, then what's going to be C dash? C dash is equal to K times of epsilon naught A by D, where K is relative permittivity or dielectric constant of the medium. So it's going to be K times of C. So can I say C dash is greater than C? Yes, it is. As C dash is greater than C, so we have two cases, right? When is capacitor is filled with mica, capacitor is filled with air. So this one I can write on capacitor in second case is greater than capacitor in first case. So if you observe and if you substitute it here, if capacitor increases, then what happens to current in the circuit? Let me show you what is happening here. So if capacitance increases, this total fraction decreases, then this complete value of denominator decreases. So if denominator decreases, then what happens to current? Increases. It means current in the second case is greater. Okay, that's the meaning. That means, so I2 is greater than I1. If current is greater, then what about voltage? Voltage in first case greater than voltage in second case. So this terminology they have given in terms of A and B. IB is greater than IA. Similarly, VA is greater than VB. Hope you understand which option matches here. VA greater than VB. Option D is the suitable answer. Got it? Next. An AC voltage is applied to a resistor capital R and an inductor L in series if R and inductive reactance are both equal to 3 ohm. The phase difference between the applied voltage and the current in the circuit. So we know the formula for tan phi. So to find out phase difference, we can use tan phi formula. So tan phi is equal to XL divided by R. They said both are equal. So XL is equal to 3 and R is also equal to 3. Then you are going to get answer as 1. So phase difference phi is equal to 45 degrees or pi by 4. So which option matches? Option B is the correct answer. Understood? Next. A coil has resistance 30 ohm and inductive reactance 20 ohm at 50 Hz frequency. If an AC source of 200 volt 100 Hz is connected across the coil, the current in the coil will be, okay, first of all we have to find out impedance, then we can find out the value of current. So let's find out XL first. So R value is 30 ohm and XL is equal to 2 pi FL. Okay, so where, let me substitute. So observe one more thing. So they are given inductive reactance itself, not inductance value. But one more thing, but the given inductance is at a frequency 50 Hz, but I need inductive reactance at 100 Hz. So let's use this method. So reactance is 20 ohms for 50 Hz. Then for 100 Hz, what's going to be reactance? For 50 Hz, reactance is 20 ohm. For 100 Hz, what's going to be reactance? Because a reactance is directly proportional to frequency, right? We can use that method. So new reactance is, so X is equal to 100 by 50 into 20. Okay, so which is equal to 40 ohm. So if you didn't understand this method, this is the trick that I've been using for proportionality relation. You can use this relation. X is directly proportional to frequency, right? Then x2 by x1 is equal to f2 by f1. Because they are given two different frequencies. Whatever the inductive reactance that they have given in the question is only for 50 Hz. But the source voltage is of 100 Hz. Then you have to find out inductive reactance at 100 Hz because inductive reactance is frequency dependent. That is the reason it will changes. So f2 is 100, f1 is 50. Then x2 is equal to, it's going to be 2. So 2 times of x1, where x1 is how much it is? 20. So you are going to get 40 ohms. Same answer I am going to get. So understood? So understand the difference here. So now I came to know what is resistance and reactance? What should I have to find out? I have to find out current in the circuit, right? So before solving it, first of all find out what is the impedance. Impedance is root of r square plus xl square, which is equal to 30 square plus 40 square, which is equal to 50. We are very familiar with this number. Now I need current. I is equal to V by Z. What's the value of V they have given? It's going to be 200 volt. So 200 volt divided by 50, which is equal to 4 ampere. Which option? Option B is the suitable answer. Got it? Next. Question number 16. Let's solve next question. In a given circuit, the reading of voltmeter V1, V2 are 300 volt each. The reading of voltmeter V3 and ammeter A respectively are. Okay. So V1 and V2 are 300 volt each. Look at this. Okay. So this is 200 volt and this is also 200 volt. Question they are asking, what's the voltage reading of V3 and current? Okay, super. So when VL is equal to VC, it means it is the circuit is under resonance. Okay, circuit is under resonance. It means inductor and capacitor are replaced with a simply short circuit. So no need to consider them. Then what's going to be current in the circuit? So definitely V3 is going to be 220 volts. There is no doubt. So supply voltage is the same as voltage across the resistor. V3 is equal to 220 volts. Voltmeter here reads 220 volts. So this is how circuit remains like. As VL is equal to VC, then the combination of capacitor and inductor is replaced with a short circuit because circuit is under resonance. This is remaining. So R is equal to 100 ohm. Vs is equal to how much it is? 220 volt, 50 hertz. What about current? This is RMS voltage and RMS current ammeter reading is equal to, so V3 divided by R. V3 is 220 volt, R is 100 ohm. So answer is 2.2 ampere. Which option? 220 volt and 2.2 amperes. Option B is the correct answer. Got it? Next, question number 17. So what is the value of inductance cell for which the current is maximum in series LCR circuit with the capacitance C is equal to 10 microfarad and omega 100 per second? Okay. Maximum current can be read in this circuit if XL is equal to XC. That means only resistance will be there. Impedance completely reduces. Impedance is nothing but opposition for flow of electrons. It is going to be reduces completely. So if XL is equal to XC, then circuit is under resonance. Then only you are going to get maximum current. So there is a condition for maximum current, that is XL is equal to XC. So hope you are able to understand. Circuit is remains with only resistor, then current is maximum. XL is omega L, XC is 1 by omega C. So from this, what about L? L is equal to 1 by omega square into C. What's the value of omega square? Omega value given. Omega is 1000. That means 1 by 1000 square is 10 power 6 into capacitance value 10 microfarad. It is 10 into 10 power minus 6. It will get cancelled. Answer is 0.1 Henry. Or else you can write down it is as 100 millihenry. Option D is the suitable answer. Understood? Next question number 18. In a circuit, L, C and R are connected in series with an alternating voltage source of a frequency F. The current leads the voltage by 45 degrees. Then the value of capacitance is, okay. So as it is a LCR series circuit, the formula for tan phi is equal to, they said current leads. That means whose effect is greater? Capacitor effect or inductor effect? Capacitor effect is greater. Then reactance divided by resistance is tan phi. That is XC minus XL, not XL minus XC, because XC effect is greater, right? So they said phi is equal to how much it is? 45 degrees. If phi is 45 degrees, then what's going to be tan phi? Tan phi is equal to 1. What should I have to find out? I have to find out the value of capacitance C. Okay, so then XC is equal to R plus 2 pi FL. XC is 1 by omega C, which is equal to R plus, I need frequency, right? In place of omega, you can write on 2 pi FC, which is equal to R plus 2 pi FL. Okay, so from this C is equal to 1 by 2 pi F into R plus 2 pi FL. Which option matches? Option D is the correct answer. Got it? Next, the value of quality factor. So we have different formulas of quality factor for series RLC circuit. That is Q is equal to omega L by R for RL circuit, and 1 by omega RC. Q is equal to 1 by omega RC for capacitor and resistor combination, and for complete all the three combination it is going to be 1 by R root L by C. So this is for series, this is for series combination. Okay, so this is for series combination. This is for RL circuit, RC circuit, and this is for RLC circuit. So if I have a parallel combination, then Q is equal to R by omega L. It will just reverse this. Then Q is equal to omega RC, and Q is equal to R into root of C by L. This is applicable for parallel combination of RLC. So this is RL circuit, RC circuit, and this is RLC circuit. Okay, are you getting the difference between them? Yes. Which option matches? Option A and option B both are suitable answers for question number 19. Okay, an LCR series circuit is connected to a source of AC current at resonance. The phase difference between applied voltage and current in this circuit is, there is no phase difference under resonance because the circuit remains with only resistor, right? So option B is the correct answer. So let's solve numericals based on the next concept, that is power in AC circuit and the power factor. Okay, so let's get started. An inductor 20 millihenry, a capacitor of 100 microfarad, and a resistor 5 ohm are connected in series across a source EMF V is equal to 10 sine 314t. Okay. But when resistance is 50 ohm, inductance is 20 millihenry, capacitance is 100 microfarad, and supply voltage V is equal to 10 sine 314t. Okay, so this is omega value. So omega is equal to 314. Okay, so the question they're asking is power loss in the circuit. This is general formula for power loss. Power loss in the sense, only loss of power will occur only in resistor. So power loss in the resistor is equal to IRMS square R. I know the value of R. Now I have to find out IRMS. To find out IRMS is equal to VRMS divided by Z. How can I find out Z value? So Z value is complete impedance of this circuit. The formula for Z is Vrms divided by root of, so what's the Z values? It's going to be R square plus XC minus XL whole square, or XL minus XC whole square. So whatever. So you are going to get complete value as positive only, right? So it does not matter here. So if they specifically mention inductive reactance is greater than capacitive reactance, you can write down XL minus XC. If capacitive reactance is greater than inductive reactance, then you can write down it is as XC minus XL. It depends. But as it is whole square, XC minus XL whole square, it's going to be completely positive, so it doesn't affect much. Now, what's the formula for XC? XC is equal to 1 by omega C, right? I know the value of omega and C also. Okay, similarly, XL is equal to omega L. Do I know the value of omega L? Omega is known and L is also known. What about R? R is equal to, what's the value? R is 50 ohms, right? So that value is also known. This is 50 ohm. If you substitute all these things, you are going to get Z approximately 56 ohms, and IRMS is equal to VRMS budget. What's the value of VRMS? So procedure to find out VRMS is Vm by root 2. So Vm is equal to root 2 times of Vs, right? Then what about Vs? Vs is equal to Vm by root 2. How to remember this? What is Vm? Vm is maximum value of voltage in the circuit, that is 10. 10 by root 2 divided by Z is 56. So which will give you answer approximately. So keep it as it is. Let's substitute in formula for power loss. Power loss P loss is equal to I RMS square R. IRMS square in the sense 10 by root 2 into 56 whole square. The R is 50 ohm, which will give you answer approximately 0.79 watt. Which option? Option A is the suitable answer. So we have to do those calculations. So there is no another way. Okay, next question number 22. So the potential differences across the resistance, capacitance and inductance are 80 volt, 40 volt and 100 volt respectively in LCR circuit. The power factor of this circuit is, so we know the formula for power factor, that is cos phi. So we have different formulas of cos phi. In terms of voltage, it is going to be, so voltage across the resistor divided by supply voltage. Supply voltage can be replaced as VR is equal to root of, so VR square plus voltage across the remaining all the terminals. Voltage across all the terminals is root of VR square. Which is greater here? Is VL is greater or VC is greater? So across resistance, capacitor and inductance. Across capacitor it is 40 and across inductor it is 100. That means VL is greater. It's VL minus VC square. So cos phi is equal to VR is, how much it is? 80 volt divided by root of VR square is 80 square plus VL minus VC, that is 100 minus 40 square. It's going to be 60 square, right? Which is equal to 80 divided by 60 square. 80 square plus 60 square is, it is going to be 10,000. That means it is going to be 100. So 0 will get cancelled. 0.8. They are asking power factor, not phase difference. So option C is the suitable answer. Next question number 23. An inductor 20 millihenry and capacitor 50 microfarad, resistor 40 ohm are connected in series across the source EMF of 10 sin 340t. The power loss in AC circuit. This question is similar to 20. So they gave all the values. Only thing we have to find out power loss. Power loss will occur only in resistor. So it's going to be IRMS square R. IRMS is Vrms divided by Z, where Z is root of r square plus xc minus xl whole square. So we know all the values. So omega value here it is 340. If you substitute R, XC and XL values, you are going to get impedance approximately. This is not I, this is Z. So Z impedance approximately it is as 65.62 ohms, and IRMS is equal to Vrms by Z, where Vrms is Vm by root 2, that is 10 by root 2 into Z is 65.62, and power loss is equal to 10 by root 2 into 65.62 whole square into R. R value is 40 ohm. So approximately you are going to get answer as 0.46 watts. Zero 0.46 is the correct answer. There is no suitable option here. Actually in the key they have given 0.51 as an answer, and maybe as it is nearer, but 0.46 watt is the correct answer. Let's move on to the next one. In an electrical RLCs and AC voltage source, all are connected in series. When L is removed from the circuit, the phase difference between the voltage and current is 5 by 3. If instead C is removed from the circuit, the phase difference between them again is pi by 3. The power factor of the circuit is equal to 1, right? Already we solved this question. Question number 24. Question number 24 is similar to which question? This one. Question number 10 and question number 24 both are similar. Okay, there is no difference. Everything is same. Next. In the instantaneous values of alternating current and voltages in a circuit are given by the average power in what's the formula for average power is P average is equal to Vrms into IRMS into cos phi. So formula for IRMS, I maximum is known. So Vrms is Vm by root 2 into Im by root 2 into cos phi. It means you can write down it is as Vm into Im by 2 into cos phi. So let's substitute them. 1 by 2 into Vm is 1 by root 2, Im is 1 by root 2, and phase difference between them is pi by 3 cos pi by 3. Cos pi by 3 is 1 by 2, 1 by root 2 into 1 by root 2, 1 by 2 again. Answer is going to be 1 by 8. Option D is the suitable answer. Okay. Next, question number 26. In question number 26, what's the question they're asking? Power dissipated in LCR series circuit is okay. In terms of EMF, they are asking. Okay, so power dissipated formula is V square by Z. Sorry, a slight change. It's not V square by Z, it's V square by R. R, I can write down it is as I square R. So that as they did mention the LCR circuit, or else you can write down one more formula, IRMS into VRMS into cos phi. Any formula is suitable here. So let's choose this. So first of all, we have to write down IRMS. IRMS is equal to ERMS divided by Z, right? So ERMS divided by Z is root of R square plus omega L minus omega into L XL minus XC 1 by omega C whole square. So this is ERMS square. Then P is equal to, let's square it. So it's going to be E square divided by R square plus omega L minus 1 by omega C whole square into R. So which option matches? Option D is the suitable answer. Understood? Next question number 27. In an AC circuit, EMF E and current I at any instant are given by this. The average power in the circuit over one cycle of AC is given by. We know that it is VRMS into IRMS into cos phi. Just now where it is, here it is. This is where same formula. Formula is E naught I naught by 2 into cos phi. So this formula is suitable. VRMS into IRMS into cos phi. VRMS is Vm by 2, IRMS is Im by, VRMS is Vm by root 2, IRMS is Im by root 2 into cos phi. So final answer is E naught I naught by 2 into sin phi. Oh, sin phi, because there is a phase difference of the given phi phase difference is there, no? It's not sin phi. Or it is cos phi. Which option? Option A is the correct answer. Sorry. So let's solve the next question. A coil of inductive reactance 31 ohm has a resistance of 8 ohms. It is placed in series with a condenser. Condenser in the sense capacitor of capacity 25 ohms. The combination is connected to AC source of 110 volts. The power factor of the circuit is, okay, they're asking power factor 28. So formula for power factor is cos phi is equal to R by Z. You can use this, or tan phi is equal to, this is one way, or else you can use tan phi. Tan phi is equal to, which is greater here, inductive reactance or capacitive reactance placed with a condenser of capacitive reactance 25, or inductive reactance is of 31. That means XL is greater, XL minus XC. Actually the total circuit behaves like inductive because XL is greater than XC divided by R. You can use any one of this, you will get the same answer. What's the value of R? Where R is 8 ohm divided by Z is root of R square plus XL minus XC whole square, which is equal to, let me substitute this. So where R value is 8 divided by root of 8 square plus XL minus XC, 31 minus 25, it is going to be 6 square. So root 8 square plus 6 square is 100, root 100 is 10, so answer is 0.8. So that's the answer. Option D is the, you can answer with the help of this also, but it is difficult because we need cos phi, right? Why should I need to find out tan phi? From this you have to find out phi, then you have to find out cos phi. It's a lengthy process, no need that. So this is enough. So this is the answer. Option D is the correct answer. Let's solve question number 29. It's no need to be solved, it's a direct question. So for a series RLC circuit, the power loss at the resonance. What is the meaning of resonance? At the resonance, only circuit consists of R. So I square R is the correct answer. So direct answer. At the resonance, XL is equal to XC. There won't be any inductance or capacitance in the circuit. So both are short circuited. Combination is short circuited. Next, 30. In AC circuit with phase difference V and I, the power dissipated in this circuit. Okay. So general formula for power dissipation is VRMS into IRMS into cos phi, right? VRMS, IRMS into cos phi. So does it depends on phase difference? Yes, definitely depends on phase difference. So option C and option D are not suitable answers because there is no phi terminology. So option B alone correct because it depends upon phase angle between V and I also. Okay, next question number 31. So in an AC circuit, the current flowing is I is equal to 5 into sine 100t minus pi by 2, okay, ampere, and the potential difference V is equal to 200 sine 100t. Okay, question they are asking average power consumption. Option 0 is correct because phase difference between them is 90 degrees. So what's the average power? P average is equal to Vrms into Irms into cos phi, where cos phi is equal to 90 degrees. So answer is going to be 0. Option B is the correct answer. Got it? Understood? Okay. So in the next part we are going to solve remaining numericals. Thank you. Have a nice day.